Okay, good morning everyone. Alright, so we will continue from where we stopped last Thursday, right? So on last Thursday we go through about the spring stiffness method. Okay, so we have gone through what actually happens behind an FEA software, okay, where we define our finite element model. Then from there the software will start to assemble the matrix, okay, then apply constraint and so on, right? It's the flow of the finite element methods, right? So today we will continue from there, okay, specifically on the assembling the matrix, right? So as we have discussed previously, okay, this particular lecture or sections, okay, this chapter itself only concentrate on using a spring as our element, right? So later on we will start to progress into using different type of finite element, right? So for now we just assume our finite element as a spring, okay? So from the spring itself we have seen these equations presented in your slides previously, okay, where we said we can assemble all the stiffness, okay, for the spring, okay, for every single spring, okay, into a single matrix, okay, or maybe we call it total stiffness matrix, right? Then also for all the forces, okay, acting on every single elements itself, okay, or the node itself is given by this, right? So we can do so-called summation of it, right? So how we can actually assemble the stiffness matrix, okay, into a single one, okay? So this is our intentions today, right? So all these steps again we will follow based on the textbook written by Professor Logan, right? Okay, so now in order to find out what is the total structure stiffness matrix, okay, for a spring assemblage, okay, assemblage itself, okay, we will use the force or maybe the displacement matrix relationship. Okay, we know that F equals to kx, right? So the x is the displacement, the F is the force, okay? So we have this kind of relationship, okay, and we can represent them in the matrix form, right? So consider a simple spring system, okay? Previously you know that for a simple spring, okay, for a single spring itself, okay, the stiffness matrix is written in this way: k minus k minus k, right? So this is only for a single spring. All right, so how we can combine them, okay, into a single assemblage or assemble them into a single matrix, okay? So we now consider two spring, okay, how we can combine them together, okay? So let's say you have two spring, okay, so we again label it, okay, this is node number 1, node number 2, and the middle one node number 3, okay? The numbering is up to you. You can number it 1 2 3, okay, or in Logan's book they put it 1 2 and 3, okay? The numbering is totally up to you, right? Then also we will number the elements number, okay? So this is the first element number 1, okay, and then here is another element number 2, right? So there is a knot connecting these two spring, okay, and at this particular knot itself, knot number 3 and knot number 4, okay, we have force acting on it, okay? So we just denote F2x, okay, along the x directions, okay, at knot number 2, as well as F3x, okay, a force acting along the x directions at the knot number 3, right? Whereas for knot number 1, we just stick it to a constraint or a wall, so no forces acting on that particular side and no displacement as well as we would expect, right? So now based on these examples, okay, two spring, two forces acting, and there is one knot, okay, being fixed at a wall, right? So how we would do later on is that we form the matrix for every single element, right? So for element number one, okay, element number one, it involves knot number one and knot number three, right? Knot number one, knot number three, and we know that from our previous derivations for a single spring stiffness matrix or relationship itself, we know that F equals to K X or displacement, right? So the displacement here refer to the displacement at knot number one as well as displacement at knot number three. Displacement 1, displacement 3, right? And then this is the stiffness matrix for a single spring, okay? So since we have more than one spring, okay, or more than one element, so in this case it's better for us to put a substrate, all right, or numbering for every single knot, every single stiffness itself, okay? So for element number one, we put K1 minus K1 minus K1 K1, right? Whereas for the force itself, okay, we would want to put what are the corresponding forces, okay, acting at every single node. So at node number one, we have F1x, okay, and we put a bracket 1 here because we want to say, or we want to know that these forces actually acting on the element number one, right? Same thing for this, okay. At this point, we put F3x, okay, acting on element number one, right? So same thing here, we put number one, okay, so that we would know where is the contribution, okay, towards the total stiffness matrix or equations later on, right? Same thing, we just repeat it for element number two. So element number two, there is knot number three, knot number two. So knot number three, knot number two, 3, 2, right? And then element number 2, 2, 2, 2, 2, and the stiffness matrix is given by K2 minus K2 minus K2 and K2, right? So we have formed the relationship for every single element, right? So we have two elements here. So now from this, remember in our sections or chapters related to the finite element software, all right, we have mentioned somewhere that the software itself, or when they combine all these elements, okay, remember there must be a knot, cannot be at the mid side and so on, right? So they actually need to comply to what we call it as continuity or compatibility requirement, right? So what it means is that this particular point, okay, or particular knot itself, okay, which connecting the element, which connect element number 1 and number 2, they must be at the same knot, okay, even though we visually know, okay, but we must tell the computer to take note on this, okay. How we tell the computer to take note of this is that whenever this knot move, okay, U3, okay, knot number 3 displace due to element number 1, the displacement must be exactly same with the displacement at knot 3 due to element number 2. They must be the same so that they move, okay. If they move 3 mm, so they must be equal number, right? So under the mathematical relationship, they must be equal, right? So this is what we call it continuity or compatibility requirement, right? Visually, as human, we can say by logic, right, that point must be same, right? But how we can tell the computer, to know all these things is through this relationship, continuity or compatibility requirement. Okay, they must be equals, right? And the number must be same with U3, right? So next would be, now we start to dissect, all right, into nodes, into element, nodes, element, and nodes, right? So here we so-called dissect, or maybe we form what we call as free body diagram. As you know, this is a very powerful method, okay, to solve any force or dynamics or statics relationship, right? So we just establish accordingly, okay? If it is not a single point, there are force acting in and out, right? So we have this capital F, okay, and there is a small f, right? So this small f represent the internal force, okay, internal force, right? Whereas the capital F, okay, represent the external force, okay, force acting on the knot itself, right? Whereas this is the internal force being reflected, okay, into the spring, right? So as we can see now, the external force must equal to the internal force at every single node, right? So they must be equal for as every single node. Why? Because they are in equilibrium, right? So if the point move to a certain point, okay, and it stop there, okay, the total summations of force acting on that particular point must be exactly equals, okay, or else there will be a net force to cause that particular node to continue to move, right? So therefore the external force here should be equals to the internal force at every single node, okay? So again, we can write the equilibrium equations at every single node itself, okay? We have this F1, okay, equals to internal force, F2 equals to internal force, and F3 a bit trickier, right? But then still tolerable, all right? We know that the summations of this force must be equals to the all the internal force acting on the at the node number 3, okay, F3 and F3 due to element number 1 and element number 2, okay? That's why we put a bracket to denote where is these contributions come from, right? They will be come from number 1, number 2, so that we will not miss out, okay, which one is which, okay? Now we can say that the F, capital F, is a result from the external applied reactions, okay? Whereas and we know that at this particular so-called wall itself, okay, wall itself, this F1, the so-called external forces, will be our reaction force, okay, acting on the fixed support, okay? So from there onwards, okay, based on our relationship, we slowly insert what is the the internal force for every single part of it, right? So how to get all these things, okay? If you derive accordingly, you should get this, right? But in a matrix form, in an easier way to visualize it, we would arrange it in the way of F3, F2, F1, okay? Then we have this particular stiffness matrix, okay, and the displacement, right? So this is where the hard work or the assemblage of the total stiffness is required, all right? So previously we have only a simple 2 equations, okay, for 2 elements, okay? Now we combine them into a single matrix, okay? And this matrix actually represented various equations, okay? And these equations actually you can work it out on your own, okay? But in the matrix form, you can actually formulate it, okay, based on certain step, okay, without the need of your intentions to maybe cancel out each other, okay, do some multiplication, minus, and so on, right? So this is what we would expect at the end, right? So if we arrange in the order of not, right, 1 2 3, then it would be in this form. Okay, so that particular form itself, if we can again check it out, right? So this form itself basically is again a capital F equals to the stiffness matrix and multiply by the displacement, right? So we have F equals to KD, right, where this is the global, now it's not element, it's now called global nodal force. Okay, this is global nodal displacement, and this is global stiffness matrix. Okay, this is where we assemble all the forces, displacement, and stiffness into a single matrix, right? And this is what the computer is doing. All right, so now come to the an easier way to do it, right? So basically you can see that I have skipped all the calculations part. Okay, I only present the idea of the matrix and how you can form this assemble or matrix is through one of the easiest way. We call it as direct stiffness method. Okay, so direct stiffness method is a convenient way, okay, by marking only the node locations. Okay, so now let's take the stiffness matrix, okay, on this particular examples, right? So we can put K element number 1, okay, equals to, as we know, K1 minus K1 minus K1 K1, right? But then this K, or maybe this element itself, is actually connected to node number 1 and node number 3. Okay, node number 1, node number 3. Therefore, we put 1 3 1 3, right, to denote it. Okay, same thing for element number 2. We have K2 minus K2 minus K2 and K2, right? And if you still recall, it's connecting, the spring is connecting node number 3 and node number 2, right? So you put U3, U2, U3, U2, okay? Put it as it is, okay? What we based on the numbering of the node connecting that particular element or spring, right? In this sense, right? So once we have formed this one, okay, what we do in this so-called direct stiffness method is that we will do a superpositions, okay? Combine them, okay? Mesh them together based on the individual element matrix. Okay, so now you can see that this U1, okay, so U1 and U1, okay, here we don't have U1 and U1, right? So when we superimpose it, then this is the only element, right? But then you can see that for, let's say, U3 and U3, all right? So U3 we have K1, okay, and here U3 we have K2. So when we combine them together, then we have to use K1 plus K2 to represent the U3 element in the matrix itself, right? So a bigger picture now. Based on this, we just total or add them up, okay, in a flow, right? So for element number 1, if we expand this, okay, to cater for U2 and U2, so basically we just add U2 and U2 here, so everything is 0 0 0, right? Whereas here we have U3 and U2, but we don't have U1, right? So if we rearrange U3 is K2, so this is K2, right? U3 U2, okay, minus K2, so U3 and U2, right? So this is minus K2, right? Minus 1 K2, right? Then this is U2 U3, so U2 and U3, so this is the locations, minus 1, and then same thing U2, U2. So U2 and U2 locations, this is 1, right? So you can see that this is how we can rearrange according to the numbering 1, 2, 3. Okay, so just make sure your numbering is correct, so you can put at the right positions of it. Okay, the rest is 0, right? So now we know that same matrix, okay, we just expand it to cater for the unused node. Okay, but then because of the unused node, there is the unused element as well, right, for the displacement and the force. But nevertheless, we just use it, and then based on this we can slowly combine, right? So this is force, this is displacement, and this is stiffness matrix, right? So when we combine it, we just total them up, right? So the total force would be F1, F2, and F3, right? So F1, F2, and F3, right? Now you can see that there are certain part we put 0 because somehow we know is 0, right? Whereas the rest we just add them up, okay? K1, K2, okay? Add them up together. So by simplifying them, okay, we can form the stiffness matrix by adding the corresponding positions or elements in the matrix. Okay, so this is how we can use it directly, right? So if we use a shortcut, right, so we can form it directly by U3, U3, this is K1, U3, U3, K2, okay, we add them up, okay, at the U3, U3 positions, okay, whereas the rest, since there are no so-called superpositions, okay, of it, then we just put at the right positions. U1, U1, we put K1, U1, U1, we put K1, right? U1, U3, we put -1, minus K1, U1, U3, we put minus K1, and so on. So we can assemble this matrix without knowing how to actually form the simultaneous equations as previous, right? So this is how we teach the computer to do things according to a certain step, right? So once we able to assemble the matrix, okay, we have assembled the stiffness matrix, we have assembled the so-called the force matrix, as well as for sure this is just a combination of both of them, right? Okay, to form the U1, U2, and U3. So based on that, now as we are aware, right, even in the quiz questions I've asked, okay, whether boundary condition will be applied before assemblage or after assemblage, right? So after you assemble it, only we put in the boundary conditions, right? So there are two types of boundary conditions. The first one would be, we call it as homogeneous boundary, and the second one would be the non-homogeneous boundary conditions. All right, so for the first one, the boundary condition, first type, is related to where certain locations we completely prevent it from moving, okay? So we would say displacement equals to 0, right? Whereas on the non-homogeneous, okay, then we have a so-called a finite non-zero value of displacement, okay? For examples, there is a movement, okay, and this particular node move to this wall, and when it reach this wall, it will stop, it will not penetrate through the wall, right? So we have this non-homogeneous boundary conditions where we may say this node will reach the wall and stop, right? So maybe the distance between the node and the wall is 5 millimeters. So the non-homogeneous boundary condition would be 5, right? A finite non-zero value. All right. So as we go through, as we continue, right? If you have questions, don't forget to put directly, okay, on the chat, right, so that we can go through it later on. Okay, so now based on again the same situations, okay, same two spring assemblage that we have previously, right? So based on the previous conditions, we know that there is u1 equals to 0. Why? Because it's not moving, right? We can see that u1, this knot is attached or fixed to the wall, right? So therefore the displacement at this particular knot is 0, right? So this is where we start to fill up our matrix. Okay, so this is where we put 0 into our matrix. Okay, so based on that, okay, since this is 0, okay, therefore we can so-called partition the matrix so such that we can only solve for this particular part, right? Because the rest, when you multiply 0, you get 0, right? This one you multiply 0, you still get 0. This one you multiply 0, you still get 0, right? So why don't we just partition this particular part, okay, and solve it, right? So this is where we call it partitions the matrix, so that we identify the part where we have sufficient unknown and non-number, right? So we have unknown and maybe non-number over there, right? Depends on what kind of boundary conditions that we know later on, right? So we can use two equations to solve for two unknown. Okay, so you can do some calculations, maybe inverse matrix and so on, to get your answer. All right. For a non-boundary conditions, okay, so this just for illustrations, okay, what it means by non-homogeneous. Okay, let's say now this particular knot is allowed to move certain displacement, okay, and we know this number of displacement, so we just put in that particular numbers into our equations, and we would continue to put in and rearrange to solve for the unknowns. Okay, but then when we include this, okay, then the situations become more complex and we need more informations, okay, in order for us to solve for the all the parameters or unknowns in the equations, right? So far, any questions before we go through one simple examples from the books? All right, still understood, right? Great, right? So now we go through into this examples, okay? After we go through it, then I hope you may try it on your own as well, okay? Just redo it, okay, so that you understand what it means, right? So in these examples, very straightforward, is there are three elements, okay, 1 2 3. We label the knots with 1 2 3 4, right? And the stiffness of every single spring is given, right? 1 2 K1 K2 and K3. Okay, so what we need is the questions asks us to find the global stiffness matrix, the first one, right? Then the second one, displacement. Third one, reaction force. Fourth one, forces in each spring. Okay, so we start with the first one. So global stiffness matrix. So global stiffness matrix, very straightforward. We can use the direct stiffness matrix equations, okay, to formulate it, right? So what you need to do is you just make sure numbering is correct. Okay, so when you do the numbering is correct, so you just write the first one, okay, the K1 minus K1 minus K1 K1, right? And we put 1 3 1 3. Is it 1 3 1 3? Yeah, 1 3 1 3. Okay, then 3 4 and 4 2. Okay, so 3 4 3 4 and 4 2 4 2. Okay, so very straightforward. Okay, so once we have this, to form the total stiffness matrix, what we need is we can just take the corresponding element, right? So 1 and 1, so 1000. Okay, so let's try. Okay, so if we form it, how many we have? We would have 1 2 3 4, right? So 1 2 3 and 4, right? So again 1 2 3 and 4, right? So at here 1 and 1 is 1000, okay, 1k, 1000, okay. And then 1 3, okay, 1 and 3 we have minus 1000, okay. Then 3 1 we have minus 1k, okay. 3 3 we have 1k, right. Now next is 3 3, all right, again 3 3, so we have, this is positive 2000, so we just add plus 2k, right. Same thing 3 4 here is minus 2, okay, right. Then 4 3 this is minus 2, okay, right. And then 4 4 2k, right, very straightforward, right. Same thing for 4 4, okay, plus 3000, okay, right. Then 4 2 here is minus 3, okay. Then 2 4 is here minus 3, okay. And 2 2 3000, 2 2 3000, right. So the rest 0 0 0 0 0 and 0, very straightforward, okay. So whatever additions we just solve it, okay. 1 plus 2, so 3k, 4 2 plus 3, okay, 5, and so on, right. So you have formed the assemblage directly, right. So you get the answer, very straightforward, okay. Just don't make mistake, right. So once we have formed that, the next one is to find what is the displacement, okay. What is the displacement at particular, okay, not number 3 and number 4, 3 and 4, right. So we want to know these two particular point, right. So what we do now, after we assemble the total stiffness matrix, we just form the relationship between force, stiffness, and the displacement, all right. So put in the boundary conditions, and we know the boundary conditions for the two ends, okay, two sides of the end, okay, they are attached to the wall, right. So 0 and 0, remember this is just an axis, all right. This is an axis, it's not a force, right. So two ends displacement is 0, so we just put in u1 is 0, u2 is 0, right. Okay, so once we know this 2 is 0, basically this part is where we have a lot of numbers, okay, or informations, okay. So we can do again partitions of matrix, okay, to solve for these two particular sides, because this one 0 0, okay, 0 0 0 0 0 0, right. So we just do a partition of it. Then at this particular point now, okay, 3 and 4, okay, in order for us to solve for the 3 and 4, again we go through 3, no external force acting, but 4 there are 5,000 pound acting on it, right. So 0 and 5,000, put it in. Now how to solve these equations, either you use MATLAB, Scilab, or mathematically using your hand, you can solve for it, right. So 0 equals to 3000 u3 minus 2000 u4, equation number 1, okay. 5000 equals to minus 2000 u3 plus 5000 u4, equation number 2. Solve them simultaneously and you would get these two displacement, right. So you can see that by using matrix, you don't need to actually arrange the equations, okay. It has been systematically grouped together in the matrix form, right. So once you get that particular displacement, now you can reinsert it, okay, then resolve back, okay, to get the remaining forces, okay. Just redo, okay, this multiply this 0 0 minus 1000 multiplied by this, and 0. So you get this one, this one, this one, and this one. Right? So if you take note again, we say summations of internal force must be equals, right? Okay, so therefore again you can double check. Okay, since for F4, okay, F4, okay, this F3 and F4 we already put 0 and 5,000, right? So if we put these equations and we get F3 and F4 not equals to 0 and 5,000, then meaning to say our calculation is wrong. Okay, but then luckily they do it right. Okay, they did it right. So F3 you get 0, F4 you get 5,000. This one 55,000 divided by 11 you get 5,000 actually, right? So they are same with this. Okay, if not, then something is wrong with your solutions over here. Okay, so double check is correct, then we can proceed to the next part. Okay, so eventually we have solved for the global nodal force. Okay, this matrix. Okay, we have solved for this one. Then finally what we need is to find the internal force, okay, for every single element. Okay, so in order to get the internal force, we just have to solve it, okay, based on the original equations. Okay, the force displacement relationship for every single elements. Okay, so we use this one. Okay, put it into our equation. So we put F1 F3 equals to this. All right, we solve, okay, accordingly. Right, repeat for second. Okay, we get this. Okay, this, and we'll notice that this internal force, they must be equals. Okay, they must be equals. Right, meaning to say if they are equals, okay, but then opposite directions, one is negative, one is positive, so you will know that for this element number 2, let's say, okay, so this is negative going in these directions, okay, whereas the F2 4 itself is positive moving to the right hand side. So meaning to say in this situation, this spring is undergoing tension, right? Because you are pulling them apart, right? Pulling them apart. Okay. Then for element number 3, we continue, but then we notice that element number 3 positive, negative, right? So force is going this way, the other force going this way. So meaning to say in this particular element, they are undergoing compression instead of tension. Okay. Compressions. Right? So we will know that based on this analysis, okay, even though we use a spring, okay, but then we know that what happens, okay, when force occurs at that particular situations, okay, which elements actually undergoing tension, compressions, and so on. Okay, so we know that this now will undergo compression, this two is under tension, right? So when we design, then this will give us some ideas what is the size of the structure that can sustain, okay, that amount of tension and compressions, right? This is why we need this kind of analysis. Okay, so that's all from me for today. Okay, so any questions? In the slide itself, okay, I have provided additional practice questions, okay, which you can go through it on your own, right? Just follow the same steps, okay, given. All right, so any questions so far? Okay, let's check. Okay, so if no questions, we will end these sessions, a very short sessions, okay, but then make sure you use the remaining time to do some practice. All right, okay, so that's all from me for today. See you again on Thursday. Okay, we will make short sessions, okay, so that it's easier for you to process, okay, throughout the weeks. Okay, so see you again. Bye bye.